have studied that matter can be divided into 3 states. Can you tell me what are these 3 categories? Yes, good. Solid, liquid and gases. We use solids most often than liquids and gases. We use utensils for cooking food. Bucket or a container used to carry water. Notebooks, pencils, papers, pens, etc. are used for different purposes. We never use the same solid for all the applications, isn't it? For different applications, we use solids with different properties. What determines these properties? The constituent particles and the type of bonds between the particles that determine the nature of specific solid. The other states of matter, that is liquid and gases, they are also known as fluids. They are known as fluids because of their ability to flow. What makes these flow is that the free movement of atoms. But the solids are rigid as the constituent particles have fixed positions in the solids. Now, if I give you a matter, for example, let us consider it as water. Can you tell me which state it is? Of course, your answer is liquid, isn't it? Now, let me ask whether it can be in its solid state, that is ice, or in the gaseous state, that is steam. To answer this particular question, that is which state is more stable for a given matter, that depends on the total effect of the 2 opposing factors. They are the intermolecular forces and the thermal energy at a particular temperature and pressure. The intermolecular forces keeps the molecules, atoms or ions closer, whereas the thermal energy makes molecules move and tends to keep them apart. Their net effect means the net effect of intermolecular forces and the thermal energy tells us about the stable state for a given matter. At sufficient low temperature, the thermal energy is very much lower and the intermolecular forces bring them very much close that they cling to one another and occupy a fixed position. They can still oscillate about their mean positions and the substance exists in its solid state. Now let us see the characteristic properties of the solids. The constituent particles. The particles can be atoms, molecules or ions. They have fixed positions. Solids have definite mass, volume and shape. The intermolecular forces are short. Intermolecular forces are very much strong that the constituent particles are arranged very much closely. The constituent particles oscillate about their mean position. They are incompressible because the space present between the atoms is much lesser. As a result of this, the solids are rigid in their structure. These solids can be classified into 2 types. One of the type is crystalline solid and the second type is amorphous solid. Crystalline solids consist of a large number of small crystals and each of them have a definite characteristic geometrical shape. And the constituent particles are arranged in an ordered manner. There is a regular pattern of arrangement of particles and this arrangements repeat itself periodically over the entire crystal structure. So, I can tell that the crystals have a long range of order. At every point, if you check, the arrangement of particles will be observed as the same. For example, we can consider sodium chloride, quartz, iron, silver, etc. All these are the examples for crystalline solids. The word amorphous is derived from the Greek word which has a meaning no form. So from this name, we tells that amorphous solids consist of particles of irregular shape. The arrangement of constituent particles. The particles can be atoms, molecules or ion. They has only short range order. In such an arrangement, a regular periodical arrangement of atom is observed only for short distances. Although amorphous solids do not possess long range regularity, but in some cases at a certain given region there follows a ordered arrangement of atoms. So this particular part of the amorphous crystal, it acts as crystalline solids, and that we term it as crystallites. The good examples for amorphous solids are glass, rubber and plastics. Here you can see the structure of crystalline quartz and quartz glass, which is the amorphous form of the quartz. The two structures are almost identical, but in the case of amorphous quartz glass, you can see that there is no long range order that is exhibited by it. Now it is clear for us that it is because of these differences in the arrangement of constituent particles we have different properties for different types of solids. So what are the differences do we observe in the properties of these different solids? Crystalline solids have a sharp melting point and they are called as true solids. Whereas the amorphous solids, they melt over a range of temperature and can be molded into the different shapes that is required for us. And they have a tendency to flow. Because of all these properties of amorphous solids, they are known as pseudo-solids, or they are also called as supercooled liquids. It is observed that glass panes fixed to the windows or doors of old buildings are found to be slightly thicker at the bottom than at its top. Can you think of why? This is because the glass flows down slowly and makes the bottom portion slightly thicker. Crystalline solids are anisotropic in nature. What is anisotropy? It means that the different physical properties, when you measure along the different directions in a same crystal, you will get the different values. For example, if you measure the physical properties such as the refractive index, you will find the different value in different direction for a crystalline solid. From this image, you can see that the arrangement of particles is different along the direction AB and it is different along the direction CD. The value of same physical property is found to be different along the direction AB and along the direction CD. Whereas the amorphous solids are isotropic in nature. It is because the arrangement of constituent atoms is irregular along the different directions. When the arrangement of particles is different along the different directions, in whatever direction you measure the physical properties, of course you are going to get the same value, and therefore the amorphous solids are isotropic in nature. Now let us summarize these differences of crystalline and amorphous solids in a table. Crystalline solids have definite characteristic geometrical shape. It is because the atoms are present in their regular arranged positions. On the other hand, amorphous solids have irregular shapes. Crystalline solids melt at a sharp and characteristic temperature, whereas the amorphous solids, they gradually soften over a range of temperatures. When crystalline solids are cut with a sharp-edged tool, they split into two pieces and the newly generated surfaces are plain and smooth. But when we cut the amorphous solid with a sharp-edged tool, the two pieces which are obtained after cutting are having sharp edges. For example, you can consider a glass. Glass is an example for amorphous solid. We often see that when glass is cut into pieces, they are cut into sharp edges and we get our hands or body parts hurt because of these sharp edges formed after cutting. The crystalline solids have definite and characteristic heat of fusion, whereas the amorphous solids, they do not have a definite heat of fusion. Crystalline solids are anisotropic in nature. Anisotropy is the different properties, physical properties measured along different directions, you will get the different values. Whereas the amorphous solids are isotropic in nature. Try to recall what is isotropy. It is the different physical properties when you measure along the different directions, you will be getting the same value. Crystalline solids are known as true solids, whereas the amorphous solids are known as pseudo-solids or supercooled liquids. Coming to the arrangement of constituent particles in crystalline solids as well as amorphous solids. Crystalline solids have a long range order, whereas these amorphous solids have only short range order. Most of the solid substances present around us are crystalline in nature. For example, the metallic elements like iron, copper, silver, and the non-metallic elements like sulfur, phosphorus, iodine, and the compounds like sodium chloride, zinc sulfate, naphthalene, etc. are found in crystalline state. These crystalline solids can be classified into 4 categories, and these classifications is based on the nature of intermolecular forces between the atoms present in the crystals. So the 4 classifications are molecular solids, ionic solids, metallic solids, and covalent solids. The constituent particles of molecular solids are the molecules. These molecular solids can be classified as non-polar molecular solids, polar molecular solids, and hydrogen bonded molecular solids. Non-polar molecular solids are formed from atoms like argon and helium, or the molecules formed by the non-polar covalent bonds. For example, hydrogen, chlorine, or iodine molecule. The atoms or molecules are held by weak dispersion forces. They are also known as London forces. And these solids are soft and non-conductors of electricity. They have low melting points and are usually present in liquid or gaseous states at room temperature and pressure. The polar molecular solids are formed by polar covalent bonds, and the molecules are held together by relatively stronger force of attraction, that is the dipole-dipole interaction. These solids are also soft and they are non-conductors of electricity. Their melting points are higher than those of non-polar molecular solids, and most of these solids are present in their gaseous or liquid state under room temperature and pressure. The examples are solid sulfur dioxide and solid ammonia. The molecules of hydrogen bonded molecular solids contains polar covalent bonds between hydrogen and fluorine, oxygen, or nitrogen atoms. The strong hydrogen bonding binds the molecules of such solids. For example, ice. The hydrogen bond between oxygen of one water molecule and the hydrogen of other water molecule binds them together. They are non-conductors of electricity. Generally, they are volatile liquids or soft solids under room temperature and pressure. As the name indicates, the constituent particles in the ionic solids are ions. The solid is composed of three-dimensional arrangement of cations and anions, which are bound by strong Coulombic forces. The Coulombic forces are nothing but they are also known as the electrostatic forces. These solids are hard and brittle in nature. They have high melting and boiling points. They are electrical insulators in the solid state. It is because in the solid state, the ions are not free to move around. But the ionic solids in their molten states or when they are dissolved in water, they conduct electricity. This is because in the molten state or when dissolved in water, the ions of the ionic solids become free and they move freely, so they conduct electricity. Metallic solids have a collection of positive ions surrounded by and held together by a sea of free electrons. These electrons are mobile, means which can move freely, and are evenly spread out throughout the crystal. Each metal atom contributes one or more electrons towards the sea of mobile electrons. The metallic solids exhibit high electrical conductivity and thermal conductivity. This is because of the presence of free and mobile electrons. The examples for metallic solids are chromium, iron, gold, silver, etc. When we apply an electric field, these free electrons flow through the network of positive ions. When heat is supplied to one portion of the metal, the thermal energy is spread uniformly throughout the metal. This is mainly because of the presence of free electrons which can move around. Another important property of metal is its luster and color in some cases. This is also because of the presence of free electrons. Also, they are malleable and they are ductile. Malleability means that we can convert them into sheets, whereas ductility refers to the property which can make thin wires from the metal. A wide range of crystalline solids of nonmetals are obtained by the formation of covalent bonds between the adjacent atoms throughout the crystal. They are also called as giant molecules. As the covalent bonds are strong and directional in nature, these atoms are held very strongly at their positions. These solids are very hard and brittle. They have extremely high melting points and they decompose before melting. They are insulators and they do not conduct electricity. A good examples for these type of solids are diamond and silicon carbide. But graphite is an exception as it is soft and a good conductor of electricity. Just now we have studied that covalent solids are hard and brittle. But what makes this graphite as soft and a good conductor of electricity? Yes, it is its structure. The carbon atoms of graphite are arranged in different layers. So this structure you can visualize from the figure that is shown here. So these carbon atoms which are present in the graphite are arranged in different layers. And the carbon atoms are covalently bonded to 3 of its neighboring carbon atom in the same layer. The 4th valence electron of each atom that is present between the different layers and they are free to move about. These free electrons make graphite a good conductor of electricity. The different layers can slide over the other, and this makes graphite a soft solid and a good solid lubricant. We shall summarize these properties of different types of crystals in a table. The 4 different types of crystalline solids are the molecular solids, ionic solids, metallic solids and covalent or network solids. We shall brief the constituent particles, the bonding or the attractive forces present between the constituent particles, examples, physical nature, electrical conductivity and melting point for each classification of crystalline solids. The molecular solids are classified into 3 types. They are nonpolar molecular solids, polar molecular solids and hydrogen bonded molecular solids. All the 3 types of molecular solids, the constituent particles are molecules. In case of non-polar molecular solids, the dispersion force or the London forces are acting between the constituent particles. The corresponding examples are argon, carbon tetrachloride, hydrogen, iodine and carbon dioxide molecule. They are soft in nature and our insulators have very low melting point. Whereas the polar molecular solids, the attraction between the constituent particles is dipole-dipole interactions. The examples are hydrogen chloride, sulfur dioxide. They are soft in nature and are electrical insulators and have low melting point. The force present between the constituent particles in case of hydrogen bonded molecular solids are hydrogen bonding. Example is ice. They are usually hard in nature, they are insulators and have low melting point. The constituent particles in case of ionic solids, as the name indicates, they are ions. These constituent particles are held together by Coulombic force of attraction or electrostatic force of attraction. Examples are sodium chloride, magnesium oxide, zinc sulfide, calcium fluoride. Their physical nature is that they are hard but are brittle. And these ionic solids are insulators in their solid state but are conductors in their molten state as well as aqueous solutions. This is because in the solid state all the constituent ions are held together, whereas in case of molten state or in aqueous solution, these ions can move freely and therefore they conduct electricity and they have high melting point. Coming to the metallic solids, the constituent particles here are positive ions in a sea of delocalized electrons. And there exists metallic bonding between the constituent particles. Examples are metals, iron, copper, silver, magnesium, etc. They are hard in nature but are malleable and ductile. They are conductors in solid state as well as in their molten state, and their melting point is fairly high enough. Moving to covalent solids or network solids, the constituent particles here are atoms. These atoms are held together by covalent bonding. Examples are quartz, silicon carbide and diamond as well as graphite. Usually they are hard in nature and are insulators, have very high melting point. An exception here is graphite, that it is soft in nature as well as it is a good conductor of heat and electricity. The reason for the conduction as well as the soft nature of graphite has been discussed already. Yes, it is the valence electron. Among the 4 valence electron, one of the valence electron is free to move about the different layers, and this free electron causes conduction in case of graphite, as well as the different layers that is present in the graphite can slide over one another. Therefore, the graphite is soft in nature. Now, you know that crystalline solids have regular arrangement of constituent particles. And you know what? This pattern repeats itself throughout the crystal structure. A portion of this arrangement of particles in a 3 dimension can be beautifully represented by this particular diagram. Each particle of the solid is depicted as a point in the figure. This regular 3-dimensional arrangement of points in a space, we call it as crystal lattice. So only 14 possible 3-dimensional lattices are present. They are called as Bravais Lattices. These crystal lattices has certain characteristics, and each point in a lattice is called as lattice point or lattice site. Each point in a crystal lattice that represents one constituent particle, which may be an atom, molecule, or it can be group of atoms or ions. Lattice points are joined by straight lines to bring out the geometry of the lattice. A smallest portion of crystal lattice, if repeated in different directions, entire crystal lattice can be regenerated. The smallest portion which is repeated itself is the unit cell. So in simple, unit cell can be described as the smallest portion of the crystal lattice. And the unit cell has dimensions along the three edges A, B and C. These edges may or may not be mutually perpendicular. The angle between the edges between the edge B and C is termed as alpha, and the angle is beta between the edges A and C. Angle is gamma between the edges A and B. Thus, a unit cell is characterized by 6 parameters: the edges A, B, C and the angles alpha, beta and gamma. These unit cells are classified into two types. They are primitive unit cells and centered unit cells. When constituent particles are present only on the corner position of unit cell, it is known as the primitive unit cell. But along with these particles at the corner position, if the particles are present at other positions, then they are known as centered unit cells. Based on the position of the atoms other than at the corner position, the centered unit cells are classified into three types. They are body-centered unit cell, face-centered unit cell and end-centered unit cells. When a unit cell contains one constituent particles, it can be atom, molecule or ion, at its body centers other than those present at the corners, it is known as body-centered unit cell. Whereas, if the constituent particle is present at center of each faces other than those particles present at the corners, then those unit cells are known as face-centered unit cells. Whereas, if this particular constituent particle which is present at center of any two opposite faces other than those particles present at the corners, then that particular centered unit cell is known as end-centered unit cells. There are 7 types of primitive unit cells. They are cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal and rhombohedral. We shall discuss about the edge length and axial angles with examples for each type of the primitive unit cells. The 7 different crystal systems are cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal and rhombohedral. The different possible variations of cubic crystal lattice are primitive, body-centered and face-centered cubic lattices. The edge lengths A, B, C are all equal in case of cubic lattices, and the axial angles alpha, beta, gamma are all equal to 90 degree. Examples are sodium chloride, zinc blende, copper. There are 2 possible variations of tetragonal crystal system. It is the primitive unit cell as well as the body-centered unit cells. Here, the edge length A is equal to B, but it is not equal to C. And all the axial angles are equal and they are equal to 90 degree. Examples are white tin, titanium oxide and calcium sulfate. There are 4 variations of orthorhombic crystal system. They are primitive unit cell, body-centered unit cell, face-centered unit cell and end-centered unit cells. Here, the edge length A is not equal to B, which is not equal to C. Means all the edge lengths are different and all the axial angles are equal and these angles are equal to 90 degree. Examples are rhombic sulfur, potassium nitrate and barium sulfate. Monoclinic system has 2 different variations. They are primitive unit cell as well as end-centered unit cell. Here, all the edge lengths are unequal and they are different. The two axial angles, alpha and gamma, are equal and they are equal to 90 degree, where beta is not equal to 90 degree. Examples are monoclinic sulfur, sodium sulfate. The triclinic crystal system, only one variation is possible, that is the primitive unit cells. Here, all the axial distances or the edge lengths are unequal and all the axial angles are unequal and they are not equal to 90 degree. Examples, potassium dichromate, copper sulfate. For hexagonal crystal system, only primitive unit cell is possible. Here, the edge length A is equal to B, but that is not equal to C. Angles alpha is equal to beta, which is equal to 90 degree, and gamma is equal to 120 degree. Examples are graphite, zinc oxide, and cadmium sulfide. Only primitive unit cell is possible in case of rhombohedral system. Here, all the axial distances are equal, that is A is equal to B, which is equal to C, and the axial angles alpha and beta are equal to gamma and they are not equal to 90 degree. Examples, calcite as well as cinnabar. It is important for us to remember all these different crystal systems along with their axial distances or edge length as well as axial angles. We have a cute mother, isn't it? So we shall remember this crystal system by relating it to our mother. So the trick here is that cute our mother. So this is the trick for us to remember these 7 crystal systems. Here, Cu represents the cubic system. Te is representing tetragonal crystal system, and this Or from our represents orthorhombic crystal system. Mo stands for monoclinic and the T stands for triclinic. He stands for hexagonal and this R stands for rhombohedral crystal system. This is how you can remember the 7 different crystal systems. So remember in this particular order. Now coming to the axial distances, in order to remember this, we shall consider which are not equal. This not equal means that the edge lengths A, B and C, whether they are equal or not equal, in which number they are equal. So here, none of them are not equal, means A, B, C are all equal. So here we have B and C which are not equal. So I mean to tell there is one not equal symbol. So here we have 2 not equals, again 2, 2, 1 and 0. Not equal 0 means all the 3 are equal. Not equal is 1 means 2 of the edge lengths are equal, that is A equal to B, whereas they are not equal to C. A, B, C all are not equal means that not equal symbol between the 3 edge lengths is 2. Again 2, one more it is 2. Then A is equal to B which is not equal to C, where the not equal symbol between the edge lengths are 1. A, B, C all are equal means that not equal symbol is 0. Axial angles are easy to remember, that in the first 3, all the 3 are equal and they are equal to 90 degree. And alpha gamma is equal to 90 degree where beta is not equal to 90 degree. Finally, all the 3 are not equal. Alpha, beta is equal to 90 degree, gamma is 120. Alpha, beta, gamma all are equal and it is not equal to 90 degree. So this is how easily you can remember the different crystal systems and their corresponding axial distances as well as axial angles. These 7 primitive unit cells in combination with different centered unit cells give us 14 different types of crystal lattices. As already mentioned, these 14 crystal lattices are called as Bravais lattices. In 14 Bravais lattices, we have 3 cubic lattices, we have 2 tetragonal lattices, we have 4 orthorhombic lattices, and we have 2 monoclinic lattices. Along with this, we have triclinic, hexagonal and rhombohedral lattices. Altogether, we have 14 different crystal lattices. We have studied that when the unit cell is repeated along the different directions, we get the crystal structure. Hence, we can tell that the crystal lattice is made up of very large number of unit cells. And every lattice point is occupied by one constituent particle. That these particles can be an atom, molecule, or it can be an ion. Now, let us calculate what would be the contribution of each constituent particle that is present at every lattice point. And hence, let us calculate the total number of atoms that is present in a unit cell. In the beginning, we shall calculate the number of atoms present in a simple cubic unit cell. So this is also known as primitive cubic unit cell. Here we have 3 different representations of primitive cubic unit cell. This structure A represents the open structure of a primitive cubic unit cell, and the structure B is known as the space filling structure. This structure represents the constituent particles in space. Structure C represents the actual portions of atoms that is belonging to one unit cell. From all these different types of structure, we can easily tell that every constituent particle is present at the different corners of the simple cubic lattice. And each of these atoms at the corners is shared between 8 adjacent unit cells that you can represent by this particular diagram. In this diagram, we have a crystal lattice that is obtained by repeating the simple cubic unit cell in the different directions. So here we have 8 different simple cubic unit cells that has been repeatedly rotated to get this particular crystal lattice. So this we can consider as one unit cell, and let me consider this as second unit cell. This is third, this is fourth. Also we have fifth, sixth, seventh and 8 unit cells that has been joined together. Now let me consider this particular unit cell here, which is numbered as 8. This is one simple cubic unit cell. Here I'll draw by this particular line. So in a simple cubic unit cell, constituent atoms are present only at the corners. So at this corner we have constituent atoms. So these are the corners where we represent the constituent atoms. So now this particular atom, you can see that it is shared with the 8 different unit cells. So, the contribution of every constituent particles that is present at each corner is 1 by 8. So, 1 by 8 is nothing but it is the contribution of each atom. It is 1 by 8. Altogether, we have 8 atoms. So, it is 1 by 8 into 8. 8 and 8 gets cancelled. So, altogether, we have 1 atom. So, I can tell that a simple cubic unit cell or a primitive unit cell, it has 1 atom in it. The value or the contribution is 1 by 8 because the constituent particle that is present only at the corners and it is shared with 8 other unit cells. So, its contribution is 1 by 8. In a cubic unit cell, we have 8 such constituent particles and therefore, the total number of atoms is 1 by 8 into 8 which comes out to be 1. Now, in the same way, let us calculate the number of atoms present in a unit cell of body-centered cubic unit cell. Here, we have the different structures for the body-centered cubic unit cell. Structure A is the open structure, structure B is the space-filling structure, and structure C represents the actual portions of atoms belonging to one unit cell. The body-centered unit cell, that is BCC unit cell, has an atom at each of its corners. We have 8 corners and 8 atoms are present at the corners and also 1 atom at its body center. From all these diagrams, you can clearly see that the atom present at the body center is not shared with any other unit cells. So that central atom is solely belonging to one particular unit cell. Thus, we can write 8 corners and the contribution of every atom at the 8 corners is 1 by 8. So, I can write 1 by 8 per the corner atom and this comes out to be 8 into 1 by 8, a total of 1 atom. Along with these corner atoms, we have 1 atom at the body center. As already told, this 1 atom at the body center wholly belongs to the one particular unit cell to which it belongs. So, the contribution of this 1 atom is 1 and therefore, we have 1 atom. So, total is 1 atom plus 1 atom. Altogether, we have 2 atoms in a body-centered cubic unit cell. Discussing about the number of atoms present in a unit cell of face-centered cubic unit cell, that is the FCC unit cells. These unit cell contains atoms at all the corners. All the 8 corners atoms are present. Along with the atoms present at the corners, at the center of all the faces of the cube, we have the constituent atoms. So here we have the open structure represented in diagram A as well as the space filling structure in B as well as in C we have actual portions of atoms that is belonging to one unit cell. As in case of the primitive cubic unit cell as well as the body-centered cubic unit cell, here also the atoms present at 8 corners, their contribution is 1 by 8. And therefore, we have 8 into 1 by 8, which is equal to 1 atom. Now, what about the contribution of the atoms that is present at the faces of the cube? Consider this atom here, which is present between the faces. Now, this atom is shared between the two unit cells. Therefore, the contribution of each atom that is present at the faces is half. We have 6 different faces. So 6 atoms are present at the 6 different faces and their contribution is half. And this comes out to be 6 into half, which is nothing but 3 atoms. So altogether, the total number of atoms that is present is 1 plus 3, which is equal to 4 atoms. So the total number of atoms that is present in a FCC unit cell is 4 atoms. So to summarize, the number of atoms that is present in a simple cubic unit cell is 1, whereas the number of atoms in case of body-centered cubic unit cell is 2, and the total number of atoms in case of face-centered cubic unit cell is 4. The constituent particles are closely packed in the crystal structure of solids. The close packing of constituent particles leaves minimum vacant space in the solids. By considering the constituent particles as identical hard spheres, now let us build the 3D structure of solids. Why to build the 3D structure? Because all real structures are 3-dimensional structures, and it is important for us to understand the 3D structure. We shall understand the building of 3D structure in 3 steps. As first step, we shall arrange these spheres in a 1-dimensional close packed structures. This arrangement can be done in only one way. What is this arrangement? Yes, it is to arrange them in a row such that the spheres are touching each other. In this arrangement, each sphere is in contact with 2 of its neighbors. So, the coordination number is 2 in 1-dimensional close packed arrangement. Wondering what is this coordination number? It is the number of nearest neighbors of a particle. In 1-dimensional arrangement, since each sphere is in contact with 2 of its neighbors, the coordination number is 2 in 1-dimensional close packing. Now, if we place the rows of close packed spheres one above the other, we can generate a 2-dimensional close packed structure. Well, this can be done in 2 different ways. How you can arrange the rows of close packed spheres? Can you think of the arrangement? Okay, let us see. One way is to place the second row in contact with the first row in such a way that the spheres of second row are exactly above the spheres of the first row. The spheres of the 2 rows are aligned horizontally as well as vertically. If we call the first row as A type of row, then the second row is exactly same as the first row, which is also A type. Similarly, we can place more rows one above the other. So we obtain A type of arrangement, as you can see here. You can see that in this arrangement, each sphere is in contact with 4 of its neighbors. So what is the coordination number in this case? Yes, you are right. The coordination number is 4 in two-dimensional close packing. Now, if the centers of these 4 neighboring spheres are joined, a square is formed. Hence, we call this packing as a square close packing in 2 dimensions. What is the other way that you can arrange these spheres? The second way is that second row may be placed above the first row in a staggered manner. Means, how do you place it? The arrangement is in such a way that its sphere fit in the depressions of the first row. So how we are going to arrange the second row? In such a way that the spheres of second row fits exactly the depressions of the first row. In this arrangement of spheres, the first row, if we call it as A type, then the second row is different than that of the first row, so we can call it as B type. When we place third row adjacent to the second in the staggered manner again, the spheres are aligned horizontally and vertically with those of the first layer. So this layer means the third layer is also same as that of the first row, that is A type. The spheres of similarly placed fourth row will be aligned with that of the second row, which is of B type. Fifth row is similar to that of the first row, A type, and similarly sixth row is same as that of the B type. Hence, the arrangement here is A, B type. Each sphere is in contact with 6 of its neighbors, and the two-dimensional coordination number here is 6 because each sphere is in contact with 6 neighboring spheres. If I join the center of 6 spheres, then they forms the corner of a hexagon. Therefore, this packing is called as two-dimensional hexagonal close packing. The hexagonal close packing is more efficient than square close packing. It is because in the hexagonal close packing arrangement there is less free space between the spheres. From the figure, you can observe that in between the layers there are some empty spaces. These empty spaces are called as voids, and these voids are triangular in shape, as you can visualize. Of course, you can see 2 different types of triangles that is present. In one row, you can see that the apex of the triangles are pointing upwards, and in the immediate next layer, you see that the apex of the triangles are pointing downwards. Let us move to see the last step towards the development of 3D structure of solids. The 3-dimensional structure can be obtained by stacking 2-dimensional layers one above the other. Just now we have discussed close packing in 2 dimensions. It can be of 2 types. What are these types? Absolutely. The square close packed structure and hexagonal close packed structure. Now, let us see what types of 3D close packing can be obtained from these 2 types of 2-dimensional close packing. We can obtain 3-dimensional close packing from a 2-dimensional square close packed layers. The second square close packed layer is placed over the first layer such that the spheres of upper layer are exactly above those of the first layer. In this arrangement of spheres, both the layers are perfectly aligned horizontally as well as vertically. In the same way, we can place more layers one above the other. If the arrangement of spheres in the first layer is called as A type, all the layers have same arrangement. So thus this particular lattice is called as AAA type pattern. The lattice so generated is a simple cubic lattice and its unit cell is primitive cubic unit cell. The three-dimensional close-packed structure can be generated from two-dimensional hexagonal close-packed layers by placing these layers one over the other. Let us take two-dimensional hexagonal close-packed layers and place them one above the other, such that the spheres of second layer are placed in the depressions of the first layer. Let us call the first layer as A type, and since we have placed the second layer such that the spheres fall at the depression of the first layer, the spheres of the two layers are aligned differently. So now let us call the second layer as B type. From the diagram here, you can see the arrangement of two layers. The bottom layer, that is A, is represented by dark red circles, and the top layer, that is the layer B, is represented by light red colored circles. From the figure, clearly you can observe that all the triangular voids of the first layer are not covered by the spheres of the second layer. Wherever a sphere of the second layer above the void of the first layer, or vice versa, a tetrahedral void is formed. Why the name is tetrahedral? It is because a tetrahedron is formed if we join the centers of the four spheres, and these tetrahedral voids are represented by the capital letter T in the diagram. Now here from these diagrams you can see the top view of the tetrahedral void as well as the exploded side view and the geometrical shape of the tetrahedral void for getting a better understanding of the tetrahedral void. At the other places, the triangular voids in the second layer are exactly above the triangular voids in the first layer, and these triangular shapes of these do not overlap. One of them has apex of the triangle pointing in the upward direction, whereas the other triangular voids have the apex of the triangle pointing downwards, and these voids are surrounded by 6 spheres, and so these voids are known as octahedral voids. Here from these figures you can see the top view of the octahedral void, the exploded side view of the octahedral void, and the geometrical shape of the octahedral void for getting a better understanding of the octahedral voids. From this diagram, clearly you can see all the tetrahedral voids which are represented by the capital letter English alphabet T, as well as the octahedral voids that are marked as capital letter O. Now if we want to know how many voids are present in the crystal structure, or how much voids are there in the given structure, to answer this particular question, this answer depends upon the number of close packed spheres. If I consider the number of close packed spheres as capital letter English alphabet N, then the number of octahedral voids generated in the crystal is also equal to N. That is, the number of octahedral voids is equal to the number of close packed spheres, and the number of tetrahedral voids generated is equal to 2n. Means the number of tetrahedral voids is twice that of the number of close packed spheres in the crystal. How we can place a third layer over the second layer now? There are two possibilities by which we can place a third layer. One way is by covering the tetrahedral voids, and the second method is by covering the octahedral voids. How we can cover tetrahedral voids. Tetrahedral voids of the second layer are covered by the spheres of the third layer. If the sphere of the third layer are exactly aligned with those of the first layer. So, if the first layer is A type, then the third layer is also of A type, whereas the second layer is B type. And this pattern of spheres is repeated in every alternate layers. This pattern often is written as ABAB pattern. This structure is called as hexagonal close packed structure. In short, it is written as HCP structure. Metals like magnesium and zinc possess this type of arrangement of atoms. Instead of this, if the third layer is placed above the second layer in such a way that its spheres covers the octahedral voids, the alignment of spheres of third layer is different than that of the first as well as second layer. So this arrangement is called as C-type. Only when the fourth layer is placed, its spheres are aligned with those of the first layer. So this pattern of layers is represented as ABC, ABC. This structure is called as cubic close packed structure, or it is also called as face centered cubic structures. In short, the structure is called as CCP or FCC structure. Metals such as copper and silver crystallizes into CCP or FCC structure. Both these types of close packing, that is the cubic close packed structure and face centered cubic structure, are highly efficient and 74% of the total space in the crystal is filled. Here, each sphere is in contact with 12 spheres. So, the coordination number is 12 in either of the two structures. We have studied that two types of voids are generated when particles are close packed to give CCP or HCP structures. The two types of voids are one is the tetrahedral void, the other is octahedral voids. Also, you know that the number of octahedral voids are equal to the number of close packed particles. So, if I consider the number of close packed particles as n, then the number of octahedral voids are equal to n. Also, the number of tetrahedral voids is twice the number of close packed particles. So, I can write that tetrahedral voids are equal to 2n. In case of ionic solids, we have cations as well as anions. Nothing but ionic solids are made up of cations as well as anions. These anions, which are bigger in size compared to that of cations, they form close packed structures, means they occupy the lattice sites. Whereas cations, they occupy voids. Voids are occupied by the cations since they are smaller in size. Now, if the cation is bigger in size, bigger in size, it occupies octahedral voids. Whereas if the cation is smaller in size, then it occupies tetrahedral voids. So in case of ionic solids, anions occupy close packed structures and cations occupies the voids. Whereas if the cations are bigger in size, they will occupy octahedral voids. Whereas if the cations are smaller in size, those cations will occupy tetrahedral sites. In case of solids, all the tetrahedral as well as octahedral voids are not occupied. Only a fraction of these voids are occupied, and that depends on the chemical formula of the compound. Now, let us understand how to identify the tetrahedral and octahedral voids occupied by the compound, and using these tetrahedral and octahedral voids, how we can write the chemical formula of a compound. Let us consider the first example. A compound is formed by two elements X and Y. Atoms of the element Y is taken as anions, make CCP, means they are forming close packed structure. And those of the elements X, which are the cations, they occupy all the octahedral voids. All the octahedral voids are occupied by element X. What is the formula of the compound? They have given that element Y makes CCP and element X, it occupies all the octahedral voids. Using this data, we need to identify what is the formula of the compound. Just now we have studied that close packed lattices are occupied by anions, and the number of octahedral voids is nothing but it is equal to the number of close packed particles. So here the number of close packed particle is nothing but it is equal to the number of elements of Y, and the number of octahedral voids is nothing but all the octahedral voids are occupied by element X. So the number of elements of X and Y are equal. So the ratios between the number of elements of X as well as Y is 1:1. So since the number of elements of X and Y are equal, their ratio is 1:1. So the formula of the element is XY. Whenever we write the formula, first we will be writing cation and then we will be writing anion, and therefore the formula is XY. Let us consider another example. Atoms of the element B forms HCP lattice, and those of element A occupy 2/3 of the tetrahedral voids. What is the formula of the compound formed by the elements A and B? In the question, they have given that HCP lattice is occupied by element B and element A occupies 2/3 of tetrahedral voids. We know that number of tetrahedral voids is equal to twice that of the number of close packed particles. And here they have given that the close packed lattice, that is HCP lattices, are occupied by element B. So I can write the number of tetrahedral voids is nothing but it is 2 times that of the number of atoms of element B. Now they have told that element A occupies 2/3 of the tetrahedral voids, and this is nothing but 2/3 of 2B, because the tetrahedral voids are given by 2B. Now let us take the ratio of atoms of elements A to atom B. So A is 2/3 into 2 times of B. Its ratio to B. So this B and B gets cancelled and the ratio is 4/B. So this is nothing but 4:3. So therefore formula of the compound is A4B3. So this is how we can find out the formula for the compound that is required. So just by knowing the tetrahedral and octahedral voids, we can write the formula of the compound that is required. The constituent particles, it can be atoms, molecules or ions. They always try to occupy themselves in the crystal lattice in such a way that less space is left vacant inside the crystals. But in whatever way these constituent particles are packed, there is always some free space in the form of voids. Packing efficiency is basically the percentage of total space occupied by the particles. That is, it tells about the total space that is occupied by the particles. So packing efficiency is calculated using the formula volume occupied by spheres in the unit cell divided by total volume of the unit cell into 100. So packing efficiency is always represented in terms of percentage. So using the formula, we can calculate the packing efficiency in different crystal structures. Let us calculate packing efficiency in case of simple cubic lattice. We know that in case of a simple cubic lattice, the atoms are located only on the corners of the cube. That you can clearly see from the 3 different structures here. That is the open structure, space filling structure, as well as the actual portions of the atoms that is belonging to one unit cell. From all these diagrams, you can tell that all the atoms are located only on the corners of the cube. And all these particles touch each other along the edge. That also you can clearly visualize from these diagrams. So here from the space filling structure, you can clearly identify that. If I consider these 4 points as the centers of the circle, so if I join all these points, I'll get the edges. So it's clear that particles touch each other along their edge. The same representation is given by this figure. Let us consider the edge length or the side of cube as A and radius of sphere as R. From this diagram, it is clear that this sphere has radius R and the other sphere has radius R. So these two are touching each other. This is one part of the cubic unit cell. So these two circles are touching at this point, and the total length of HA is nothing but it is the edge length or you can consider this as side of cube, that is equal to A. So clearly you can tell that A is twice the radius of the sphere. So the formula to calculate packing efficiency is volume occupied by the atoms in the unit cell divided by volume of the unit cell multiplied by 100. So this gives us packing efficiency in terms of percentage. For this cubic lattice, let us find the volume occupied by the atoms as well as volume of the unit cell. So for cubic lattice, volume of unit cell is given by A cube. So A is 2R. So this is 2R cubed. So we get 8R cube as the volume of unit cell. Since the atoms are represented as spheres, volume of the atoms is equal to 4 by 3 pi r cube, which is the volume of the sphere. Number of atoms in a simple cubic lattice is equal to 1, and therefore the total volume occupied by the atoms is equal to 1 into 4 by 3 pi r cube, which is equal to 4 by 3 pi r cube. Now let us substitute these things into the formula of packing efficiency. Volume occupied by the atoms is 4 by 3 pi r cube. Volume of the unit cell was A cube, and we have calculated it as 8 r cube into 100. R cube and R cube gets cancelled with one another. Further simplifying this, we get the packing efficiency as pi by 6 into 100. This is 52.36%, and approximately we can write this as equal to 52.4%, and therefore the packing efficiency in case of simple cubic lattice is 52.4%. Now let us calculate the packing efficiency in case of body-centered cubic structure. Here in these diagrams, you can see the different structures of body-centered cubic unit cells. You have the open structure, space-filling structure, as well as the structure that represents the actual portions of the atoms belonging to unit cell. And we all know that there are 8 atoms that is present at the 8 corners, as well as at the body center 1 atom is present in BCC unit cell. From this diagram here, you can clearly see that atom that is present at the center here, that is in touch with the other 2 atoms diagonally. Here also let us consider the edge length or the length of sides of cube as A, as well as radius of the spheres as R. In the BCC structure, we have 2 types of diagonals. One is the body diagonal. The other is face diagonal. In order to understand about the body diagonal and the face diagonal, let us consider this particular cube. This cube has 6 faces. Let me consider this as face 1, this is face 2, this is 3, this is 4. To the front side, this is 5th one, and at the back side, this is the 6th one. So these are the 6 different faces of a cube. And a diagonal that is present in a face. So if I consider this particular face, face 1 which I have represented, a diagonal, if I join this A and B, I will get a diagonal. And this diagonal AB is the face diagonal. What is body diagonal then? Again, I have drawn a cube here. Now, if I join the points A and D, that is a diagonal passing through the body center of the unit cell, is nothing but the body diagonal. So here AD is the body diagonal of the cube. In this diagram here, B is the face diagonal and C is the body diagonal. So the body diagonal is C in the diagram, as well as the face diagonal is represented by B. Now let us write this body diagonal as well as the face diagonal in terms of the edge length A. In the triangle EFD, since we have one angle 90 degree, we can write that the face diagonal B square is sum of A squares, and this is 2A square. Therefore, B is square root of 2A. Now we need to find the value of C in terms of edge length A. For that, we shall consider the triangle AFD. So triangle AFD has to be considered. It is also a right angle triangle. So we can write the diagonal C square is the sum of A square plus B square. B square is 2A square, and therefore C square is 3A square. This means that C is nothing but square root of 3A. Now if you consider this body diagonal AF, this part is radius of the sphere and the sphere at the center is completely there. So it is 2 times the radius and half of the other sphere. So its radius. So length of the body diagonal is equal to 4r. So I can write the length of the body diagonal, which we have considered as C, is nothing but it is equal to 4 times the radius of the sphere. This I can also write that root 3a is equal to 4 times the radius. From this we can write the radius of the sphere is root 3a divided by 4. So now we have calculated radius of the sphere in terms of the edge length. Now let us calculate the packing efficiency by substituting these values into the formula of packing efficiency. The total number of atoms present in a BCC unit cell is 2, and the volume occupied by one atom is 4 by 3 pi r cube. volume of unit cell is given by A cube. So here we have written A in terms of the radius. From the expression R is equal to root 3 by 4A, we can write A is nothing but 4 into R by root 3. So A cube is nothing but 4 by root 3 into R whole cube. Now let us substitute these values into the formula. And therefore, packing efficiency is equal to volume occupied by the atoms is 2 into 4 by 3 pi R cube divided by volume of unit cell, that is 4 by root 3 into R whole cube into 100. Simplifying this, we get the packing efficiency as 68%. In the similar way, now let us calculate the packing efficiency in case of HCP and CCP structure. Both these structures are equally efficient. Now, let us calculate the packing efficiency in case of CCP structure. Here, the edge length is considered as A, as well as the radius of spheres is taken as R, and also we have considered the face diagonal, that is taken as B. So this face diagonal B is represented by AC in the diagram. If we consider the triangle ABC in this figure, we can find out the value of face diagonal. So from this triangle ABC, we can write AC square as the sum of AB square and BC square. So this is B square is the sum of AB square and BC square, and this is equal to 2A square. And therefore, B is nothing but it is square root of 2A. Also from this diagram, since this is representing the radius, I can write B is nothing but it is 4 times the radius. So we have already calculated B is square root of A, and that is equal to 4R. So from this I can write radius of the sphere is root 2 divided by 4 into A. Or I can write A as 4 by root 2 into R. This can be simplified and written as 2 root 2 R. Just to make this simplification clear, I'll do the simplification part here. This is 4 by root 2. So 4 I can write this as 2 into 2 divided by root 2. Now, one of the 2's I can keep it as such, and the other I'll write it as square root of 2 into square root of 2. So root 2 into root 2 is nothing but it is root 2 square. So square and square root gets cancelled. We get it as 2 divided by root 2. So one root 2 and the other root 2 on the numerator get cancelled. So we get 2 into square root of 2. So this is how you can simplify. Now we know that each unit cell has 4 atoms. The volume occupied by the atoms means the total volume of the unit cell is 4 into 4 by 3 pi r cube, and volume of unit cell is A cube, and this is equal to 2 root 2 into R cubed. Now let us substitute these two volumes into the formula of packing efficiency to find out what is the percentage of the packing efficiency in CCP unit structure. Substituting, the volume occupied by the atoms is 4 into 4 by 3 pi r cube divided by volume of the unit cell is a cube into 100. So 4 into 4 by 3 pi r cube divided by a cube, that is 2 root 2 r cubed. Simplifying this, we get the packing efficiency as 74%. Now, if we are provided with unit cell dimensions, we can calculate the volume of the unit cell. If the density of the metal is known, we can also calculate the mass of atom in the unit cell. How to calculate all this? Come, let's see it. Let us consider the edge length of a unit cell as A, and we shall consider density as D. Also, we shall consider M is the molar mass of the solid. Now, if I consider a cubic crystal, for a cubic crystal, we have its volume. So, volume of unit cell is given by A cube. Also, we can calculate the mass of unit cell. Mass of the unit cell depends on the number of atoms present in that particular unit cell as well as mass of each atom. So, if I consider Z as the number of atoms present in a unit cell, and if I consider small letter alphabet M as mass of that each atom, then mass of unit cell is given by Z into M. So, here Z is the number of atoms present in one unit cell. And M is the mass of one atom present in the unit cell. So, mass of the single atom is nothing but it is the molar mass divided by Avogadro number. And I can write density of the unit cell as D is equal to mass of the unit cell divided by volume of the unit cell. So, density is nothing but mass by volume. So, mass of the unit cell is given by Zm. Volume of the unit cell is given by A cube. So, mass of unit cell can be written in terms of the molar mass. So, that is Z into molar mass M divided by A cube into Avogadro's number. So, this particular formula D is equal to Z into M divided by A cube into Na gives the density of unit cell. So, density of unit cell is nothing but it is same as the density of the substance. Out of these 5 parameters, that is density, number of atoms in a unit cell, molar mass, edge length as well as Avogadro's number, if any 4 of this is known, fifth quantity can be determined. Now, let us consider an example for calculations involving the unit cell dimension. The question is, an element has a body-centered cubic structure with a cell edge of 288 picometer. The density of the element is 7.2 gram per centimeter cube. How many atoms are present in 208 gram of the element? They have given the edge length as 288 picometer. Edge length is represented by A, so that is 288 picometer. So we shall write this in the SI unit, meter. So it is 288 into 10 to the power minus 12 meter. Also they have given density represented by D is equal to 7.2 gram per centimeter cube. Since the density is given in the unit of centimeter cube, we shall convert this meter into centimeter. So 288 into 10 to the power minus 10 centimeter. In the question, they have asked us to identify the number of atoms present in 208 gram of the element. We know that in a BCC structure, in one unit cell, we have 2 atoms. Now the task for us is to find the number of atoms present in 208 gram of the element. So we know that number of atoms in one unit cell of BCC unit cell is 2 atoms. So in 208 gram of element, how many atoms are present need to be calculated. So in order to find the atoms, we need to calculate the total number of unit cells in 208 gram of the element. So let us see how we can find it out. So we need to find the total number of unit cells in the 208 gram of element. We are provided with edge length, so we can calculate volume of one unit cell. Volume of one unit cell is nothing but it is a cube. So we have edge length, that is 288 into 10 to the power minus 10 centimeter, its cube, and this comes out to be 2.39 into 10 to the power minus 23 centimeter cube. In the question, we are also provided with density as well as mass of the element. Density is 7.2 gram per centimeter cube as well as mass of the element, that is given 208 grams. So we can find the volume of the given element. So volume of 208 gram of element, this is equal to mass upon density. So mass is 208 gram, density is 7.2 gram per centimeter cube, and the volume is equal to 28.88 centimeter cube. Now here we know that volume of one unit cell is 2.39 into 10 to the power minus 23 centimeter cube, and we have volume of 208 gram of element. This is equal to 28.88 centimeter cube. So knowing these two values, we can calculate the total number of unit cells that is present in 208 gram of element. And therefore, number of unit cells in 28.88 centimeter cube of the element is equal to 28.88 centimeter cube divided by 2.39 into 10 to the power minus 23 per unit cell. And this comes out to be 12.08 into 10 to the power 23 unit cells. So in the given 208 grams of the element, we have 12.08 into 10 to the power 23 unit cells. But they have asked us to find the total number of atoms. So one unit cell of PCC unit cell, it consists of 2 atoms, and therefore total number of atoms is 2 times that of 12.08 into 10 to the power 23, and this is equal to 24.16 into 10 to the power 23 atoms. And this is the answer for our question. Hoping that you are enjoying this study on the structure of crystals. Now we shall study about the defects in the crystals. The solids are made up of large number of small crystals, and these small crystals have defects in them. Defects? What are these defects? Crystals have regular and ordered arrangement of constituent particles, but these arrangements are missing somewhere in the crystals, and this results in the irregularity. Why this happens? Why the irregularities in atoms exist in crystals? The process of formation of crystals, and this process we call it as crystallization. The rate of crystallization is sometimes occurs very slowly, sometimes the crystallization occurs very fast. Because of these reasons, defects occur in crystal. Now we shall discuss the different types of defects in the crystals. Broadly telling, the crystal defects are of 2 types. They are point defects and line defects. From the name itself, we can understand that point defects are the irregularities around a particular point or atom in a crystal. The line defects are the irregularities in the entire row of the lattice points. We shall limit our discussion only to the point defects. The point defects are classified into 3 types. They are the stoichiometric defects, impurity defects, and non-stoichiometric defects. Stoichiometric defects are the point defects that do not disturb the stoichiometry of the solid. Stoichiometry do not change. What does this mean? Say, for example, a crystal is made up of 2 atoms, X and Y. How many atoms of X and Y are present before the same number of atoms of X and Y will be present after the defects originate in the crystal? For example, let us consider sodium chloride, that is NaCl. The number of atoms of sodium as well as chlorine which are present before the formation of defects in the crystal, as well as the number of atoms of sodium and chlorine which are present after the defects originate, they remains the same, and therefore the stoichiometry do not change. These defects are also called as intrinsic defects, or they are also called as thermodynamic defects. These defects are of 4 types: vacancy defects, interstitial defects, Schottky defect, and Frenkel defect. Vacancy defect, what is this? The name itself tells that some of the lattice sites are vacant. What is present in the lattice sites of crystals? Of course, particles, right? It can be atoms, molecules, or ions that are present in the lattice site. When these lattice site is left vacant or when the lattice site is empty, it creates vacancy defects. Usually, vacancy defects are produced in solids by heating them. What happens to the solids because of this vacancy defects? Density of the substances will decrease. For example, let us consider a simple cubic lattice. In a simple cubic lattice, the constituent particles are present at the 8 corners of the cubic lattice. If one of the lattice site is empty, of course the density has to decrease, isn't it? So that is why the vacancy defects decreases the density of the solids. The second type is interstitial defect. These defects are observed when some constituent particles, it can be atoms or molecules, occupy an interstitial site. What is the meaning of interstitial site? You know, in a crystal lattice, the atoms are present at the lattice site and the space between the lattice points is known as interstitial site. Some constituent particles occupy these interstitial sites, so the defects are called as interstitial defect. Now, here the atom occupies interstitial site. Can you tell me what will happen to the density? Density increases, right? Because more number of atoms are present in small region. These vacancies and the interstitial defects are observed in non-ionic solids. The third type of stoichiometric defect is Frenkel defect. These defects are usually observed in ionic solids. These defects occur when smaller ion, usually it is cation, leaves its normal site and it occupies the interstitial site. As a result of this, vacancy defect is created at its original site. What will happen in its new location? So since the cation is moving into the interstitial site, it creates an interstitial defect in the new site. So this type of defect is also called as dislocation defect because the ion is dislocated from one site to the other. This defect do not change the density of the solid because the cation was present before as well as after the origin of the defect. The cation did not escape from the solid. So the density neither increases nor it decreases. Frenkel defect is exhibited by ionic substances in which there is large differences in the sizes of atoms. For example, zinc sulfide, silver chloride, silver bromide and silver iodide exhibit Frenkel defect. This is because of the small size of Zn2 plus as well as Ag plus ions in comparison with that of the anions. The fourth type of stoichiometric defect is Schottky defect. These defects are also present in the ionic solids. The ionic solids in which the cation and anion are almost similar sizes. Understand that this is a vacancy defect in ionic solids. What happens here? It is a cation and anion is missing from the lattice. The number of missing cations and anions are equal. So, as these cations are missing, vacancy is created in the solids. So, this defect is called as vacancy defect. So, the vacancy defect in ionic solids is called as Schottky defect. It is important to remember that Schottky defect is shown by ionic substances in which cation and anion are almost similar in sizes. For example, Schottky defect is exhibited by sodium chloride, potassium chloride, cesium chloride as well as silver bromide. Also remember that the number of missing cations and anions are equal. Why? It is to maintain the electrical neutrality. In all the defects we have discussed, electrical neutrality is maintained. Though the ions are moving here and there and escaping from their sites, they may occupy the interstitial sites also. But the overall neutrality of the solid is always maintained as the cations and anions are missing. Like the simple vacancy defect, Schottky defect is also decreases the density of the substance. Now if we compare the Frenkel defect and the Schottky defect, both the defects are observed in ionic solids, but Frenkel defect is observed in ionic solids where the size of cation is small compared to that of the anion. And this cation leaves its side and it occupies the interstitial site. On the other hand, Schottky defect is observed where the cations and anions have comparable size. For example, you can consider sodium chloride. Na plus and Cl minus have comparable size. Frenkel defect do not change the density of the solids, whereas Schottky defect, it decreases the density of the solids. Now we are going to discuss the impurity defects. From the name itself, you can make out that some impurity atom or the foreign substance is coming into existence in this case. Means that in the lattice structure, an impurity atom is occupying the lattice point. For example, if we consider sodium chloride, that is NaCl. In the structure of NaCl, we observe only sodium and chlorine atoms. Now, if by moving some sodium atoms, some other atoms occupies its position, this defect is known as impurity defect. How this happens? We will consider the example of sodium chloride itself. During the crystallization of sodium chloride, if a little amount of strontium chloride is added to molten sodium chloride, some of the sites of Na plus ions are occupied by Sr2 plus ions. We can see Sr2 plus ions in the place of Na plus in some of the lattice sites. Now we know that electrical neutrality has to be maintained. Here Sr2 plus is replacing Na plus. Na is having plus 1 charge and Sr is having plus 2 charge. How to make these charges equal in order to maintain the electrical neutrality? Each strontium 2 plus replaces 2 Na plus ions, and the strontium 2 plus ion occupies the site of one Na plus ion and the other site of Na plus ions remains vacant. Now this creates a vacancy. This type of defect we call it as impurity defect. These cationic vacancies thus produced are equal to the number of strontium 2 plus ions. The other type of defect we are going to discuss is the non-stoichiometric defect. From the name non-stoichiometric defects, we can understand that these defects disturb the stoichiometry of the solids. Means it disturbs the cation to anion ratio in the solids. Now, it's not necessary that the number of cations and the number of anions that are leaving are equal to the number of cations and the number of anions entering the crystal structure. But it's important to remember that the electrical neutrality should be maintained. These non-stoichiometric defects are of two types. One is metal excess defect and the second type is metal deficiency defect. At first we will discuss the metal excess defect. From the name itself, we can tell that metals are present in excess. Metals are the donors of electrons and are always ready to give electrons, and they become positive ions. So what will be excess? Yes, the cations, that is the positively charged ions, will be present in excess. Can you think of how these metal excess defects will arise? We need cations in excess. So we can do two things. One is that we can remove anions, so we can create an ionic vacancy. And the second option is to add extra cations to the interstitial sites. At first, let us discuss how we can create anion vacancy. For example, let us take sodium chloride crystal. Now, in order to create excess cations, we need to remove Cl- ions. How we can remove the Cl- ions? For this reason, we will pass sodium vapors through NaCl crystals. These sodium vapors will lose its electron and form Na+. This Na+ attracts the Cl-. The Cl- is attracted from the crystal, will move towards the Na+. So inside the crystal, a vacancy is created at the place of Cl- ion, and the electron which is obtained by the ionization of sodium vapors, they occupy the vacant site. Electron is not an anion. Therefore, the number of anions is lesser inside the crystal, and cations are present excess inside the crystal. So, this type of defect is called as metal excess defects. Also, we told that this is a non-stoichiometric defect. Why? Here, the cation and anion ratio is disturbed because of the escape of Cl- ion. Now, you will ask how the electrical neutrality is maintained. The electrical neutrality is maintained because the electron obtained by the ionization of sodium vapors, they occupy the vacant site of Cl- ion. And this is how the electrical neutrality is maintained. So, the stoichiometry is disturbed, but the electrical neutrality is still maintained. So, the metal excess defect here is caused because of the anionic vacancy. I told you that the anionic sites are occupied by the electrons. Electrons which are obtained by the ionization of sodium vapors. And these anionic sites where the electrons are occupied are called as F centers. These electrons absorb energy from visible light falling on them and undergo excitation. They emit radiation. This imparts yellow color to the crystals of sodium chloride. Similarly, excess of lithium makes lithium chloride crystals pink, and excess of potassium makes potassium chloride crystals violet or lilac in color. Now we shall see how metal excess defects can be achieved by the presence of extra cations at the interstitial sites. For example, let us consider ZnO, that is zinc oxide. The structure of zinc oxide has Zn2 plus and O2 minus ions. When zinc oxide is heated, it loses oxygen and it gives Zn2 plus. These cations which are obtained in excess, where do they go? They occupy the interstitial sites. The number of Zn2 plus ions increases and the ratio of cation to anion will also increase. So, this is obviously the non-stoichiometric defect. How the electrical neutrality is maintained? This is a question now. The electrons obtained during the heating of zinc oxide will occupy the interstitial sites along with the cations, and this maintains the overall electrical neutrality. Here, the ratio of cations to anions is disturbed because of the number of certain 2+ ion increases and the number of oxygen decreases. At the same time, the number of cations increases, means metal is in excess. So, this defect is metal excess defect. We shall discuss the second type of non-stoichiometric defect, that is the metal deficiency defect. Again, from the name, the metal deficiency means metals will be deficient. That is, the cations are lesser in number here. These defects are observed when metal which exhibits the variable valences. For example, iron. +2 and +3 valencies are exhibited by iron. Let us consider iron oxide, that is FeO. We have the cations Fe2+ and the anions O2-. Now, if we replace Fe2+ with Fe3+, what will happen? Electrical neutrality should be maintained. 2 Fe3+ can't replace 3 Fe2+, because 2 Fe3+ has 6 charge and 3 Fe2+ has +6 charge. So, they can replace each other. So, we will remove 3 Fe2+ and we will add 2 Fe3+. Now, the electrical neutrality is maintained, but the ratio of cations to anions is disturbed. Previously, 3 charged cations were present and now we have only 2 charged cations. What is happening here is the cations are decreasing and the metal is becoming deficient. So, the name is metal deficiency defect. After understanding about the structure of solids and defects in solids, now let us discuss the electrical properties of these solids. The solids are classified as conductors, insulators and semiconductors on the basis of their conductivities. The solids with the conductivities ranging between 10 to the power 4 to the 10 to the power 7 are called as conductors. The good conductors are those metals having conductivities in the order of 10 to the power 7 ohm inverse meter inverse. Insulators are the solids with very low conductivities ranging between 10 to the power -20 to 10 to the power -10. Whereas the intermediate between these conductors and insulators are the semiconductors, and they have conductivity range from 10 to the power -6 to 10 to the power 4. A conductor conducts electricity due to the movement of electrons or ions. The metals conduct electricity because of the movement of mobile or the free electrons present in them, whereas the electrolytes conduct electricity because of the movement of ions present in them. It's interesting to know that how these substances conducts electricity. The molecular orbitals formed by the overlapping of atomic orbitals of metals are so close in energy that these energy levels overlap with one another and they form a band. This band is known as valence band. It is because the valence electrons are present in these bands. The conductivity of metals depends upon the number of valence electrons available per atom. If the valence band is partially filled, or if the valence band overlaps with the higher energy unoccupied conduction band, then the free electrons that are present can flow easily from the valence band to the conduction band under the application of electric field, and this is how the metals shows conductivity. On the other hand, if the gap between the filled valence band and the next higher unoccupied band, that is the conduction band, is large, means the gap between the valence band and the conduction band is larger, electrons cannot jump from valence band to the conduction band. So what will happen? The substance will have small conductivity and it behaves as an insulator. Hope you have understood how the conductors and insulators conduct electricity. What happens with the semiconductors, the ones which are the intermediates between the conductors and insulators? In case of semiconductors, the gap between the valence band and the conduction band is small. As a result, some electrons from the valence band jump into the conduction band and they show some conductivity since the energy gap is small. Now, if we increase the temperature, what will happen? We can send some more electrons from the valence band to the conduction band, and this increases the conductivity. So, I can tell that the electrical conductivity of semiconductors can be increased by increasing the temperature. Examples for these type of semiconductors are silicon and germanium, and these semiconductors are also called as intrinsic semiconductors. The conductivity of these intrinsic semiconductors is too low. As a result, they cannot be used for the practical applications. Somehow, their conductivity has to be increased. So, what can be done to increase the conductivity of intrinsic semiconductors? The conductivity of intrinsic semiconductors can be increased by adding appropriate amount of the electron rich or electron deficient impurity. And this process of adding a suitable type of impurity to enhance the conductivity of intrinsic semiconductor is called as doping. These impurities that are added to the intrinsic semiconductor introduces electronic defects in them and increases the conductivity of intrinsic semiconductors. Now, let us see which are the electron rich impurities and which are the electron deficient impurities that can be added to silicon or germanium to increase their electrical conductivity. Do you know to which group of the periodic table does silicon and germanium belong to? Yes, silicon and germanium belong to group 14 of the periodic table, and they have 4 valence electrons each. In their crystal structure, each atom forms 4 covalent bonds with its neighbors. When the silicon or germanium is doped with a group 15 elements like phosphorus or arsenic, which contains 5 valence electrons. These impurities, that is phosphorus or arsenic, occupy some of the lattice sites in the silicon or germanium crystal when it is added. 4 out of the 5 valence electrons of phosphorus or arsenic are used in the formation of 4 covalent bonds with the 4 neighboring silicon or germanium atoms. What about the 5th electron? The 5th electron is extra and it becomes free. So, this delocalized electron is increasing the conductivity of doped silicon or germanium. So, what increases the conductivity of intrinsic semiconductor, silicon or germanium? Yes, here the increase in the conductivity is due to the negatively charged electron. Hence, silicon or germanium doped with electron-rich impurity is called as N-type semiconductor. On the other hand, we can dope silicon or germanium with group 13 elements like boron, aluminium or gallium, which contains only 3 valence electrons. Here, an electron is missing for the bond formation. The place where the 4th valence electron is missing is called as electron hole or electron vacancy. An electron from the neighboring atom comes and fills this electron hole. But in doing so, this creates a vacancy for electron at the original position, resulting in the displacement of electron hole in the direction opposite to that of the electron that has filled it. When electric field is applied, electrons would move towards the positively charged plate through electronic holes, but it would appear as if the electron holes are positively charged and are moving towards negatively charged plate. This type of semiconductors are called as p-type semiconductors. These n-type and p-type semiconductors are used in various combinations for making electronic components. Diode is such a combination of n-type and p-type semiconductor, and it is used as a rectifier. Transistors are the devices manufactured by sandwiching a layer of one type of semiconductor between two layers of the other type of semiconductors. We have a p layer that is sandwiched between two n types called as NPN transistors, and PNP transistors where a n-type layer is sandwiched between two p-type layers. These transistors are used to detect or amplify the radio or audio signals. The solar cell is an efficient photodiode that is used for the conversion of light energy into the electrical energy. Gallium arsenide is a semiconductor that has very fast response and have transformed the design of the semiconductor devices. Transition metal oxides show a marked differences in their electrical properties. Titanium oxide, chromium oxide and rhenium oxide behaves like metals. Rhenium oxide resembles metallic copper in terms of its conductivity as well as appearance. Certain other oxides like the oxides of vanadium as well as the oxides of titanium exhibit metallic or insulating properties depending on the temperatures. Every substance has some magnetic properties associated with it. Based on these magnetic properties, substances are classified into 5 categories. They are paramagnetic substances, diamagnetic substances, ferromagnetic substances, antiferromagnetic substances and ferrimagnetic substances. Before understanding about these classifications, let us try to understand how these substances exhibit magnetic properties or what causes these substances to show magnetic behavior. The origin of the magnetic properties in the substances lies in the electrons. Each electron in an atom behaves like a small tiny magnet, and these electrons move around the nucleus. It is called as orbital motion. And also the electron spins around its own axis, and these two types of motion generates magnetic moment in the substance. Electron being a charged particle and undergoing these motions, it can be considered as a small loop of current which possesses a magnetic moment, and therefore each electron has a permanent spin and an orbital magnetic momentum that is associated with it. The magnitude of this magnetic moment is very small and is measured in the unit called as Bohr magneton. And we have 1 Bohr magneton is equal to 9.27 into 10 to the power minus 24 amps per meter square. Now let us discuss the classification of substances based on these magnetic properties. The first classification we are going to discuss is paramagnetism. The paramagnetic substances are weakly attracted by a magnetic field. They are magnetized in a magnetic field in the same direction. When the magnetic field is removed, the magnetism is lost by the paramagnetism substances. The paramagnetism is due to the presence of one or more than one unpaired electrons in the substances, and these electrons are attracted by the magnetic field. The examples for paramagnetic substances are oxygen, copper 2+, iron 3+, chromium 3+. The second type is diamagnetism. Diamagnetic substances are weakly repelled by a magnetic field. Examples are water, sodium chloride and benzene. They are weakly magnetized in a magnetic field in the opposite direction. Diamagnetism is shown by those substances in which the electrons are paired and there is no unpaired electrons in the substances. Pairing of electrons cancels their magnetic moments and they lose their magnetic character. A few substances like iron, cobalt, nickel, gadolinium and chromium oxide are attracted very strongly by a magnetic field. Such substances are called as ferromagnetic substances, and these substances can be permanently magnetized. In the solid state, the metal ions of the ferromagnetic substances are grouped together into small regions, and these regions are called as domains. Each domain here acts as a tiny magnet. In an unmagnetized piece of ferromagnetic substances, all these domains are randomly oriented and their magnetic moments get cancelled. When these substances are placed in a magnetic field, all these domains get oriented in the direction of the magnetic field, and a strong magnetic effect is produced because of this orientation. Now, this ordering of domains persists even when the magnetic field is removed, and these ferromagnetic substances become a permanent magnet. Certain substances has domain structure that is similar to that of ferromagnetic substances, but their domains are oppositely oriented and cancels out each other's magnetic moment, and these substances are known as antiferromagnetic substances. Example is manganese oxide. Ferrimagnetism is observed when the magnetic moments of the domains in the substance are aligned in parallel and anti-parallel direction in unequal numbers. As you can see that from the figure. They are weakly attracted by the magnetic field as compared to that of ferromagnetic substances. Magnetite as well as ferrites are the examples of antiferromagnetic substances. These substances also lose ferrimagnetism on heating and they become paramagnetic in nature. Hereby we complete the chapter on solid state. If you haven't watched our other videos, you can watch it by clicking on the playlist link here. Thank you for watching. Stay connected, keep learning. We shall meet in our next video. Take care. Bye-bye.